In this video, we will look at three rules of exponents, sometimes also referred to as exponent laws. These rules are essentially shortcuts for expressions that involve both multiplication and exponents. To understand where the rules come from, as well as why the rules are what they are, you must understand what an exponent is representing. And that's where we begin with any of these rules. In part A, we want to simplify x to the third times x to the fourth. To understand how to do this, we need to stop and think about what does the expression x to the third mean. It means that we're going to be multiplying x by itself 3 times. And we're going to be multiplying that by x to the fourth. On its own, x to the fourth means we're multiplying x by itself 4 times. Since an exponent only means repeated multiplication, and once I expand out what x to the third and x to the fourth represent, I see that I have a total of 7 x's. I know that this can be simplified down to x to the 7th power. In part B, we have 7 to the 6th times 7 to the 5th. 7 to the 6th means I will be multiplying 6 7s together. Separately, 7 to the 5th means I will have 5 7s. If we look across this expression, I now have 6 7s multiplied by 5 more 7s. So in total, I'm multiplying 11 7s together, and this can be reduced down to the expression 7 to the 11th. Now the idea is that we don't always want to do this. We don't want to have to write out these exponents for what they mean. The point of the exponent is to keep things more compact. So what we want to find is a pattern here. I notice in part A I started with 3 x's and multiplied by 4 more x's and obtained 7 x's in the end. In part B, I had 6 7s, I multiplied that by 5 more 7s, and I had in the end a total of 11 7s. So looking at part C, I want to do this without writing out what all of these expressions mean. W squared times w to the third times w to the fourth. I know I have 2 w's multiplied in the front, 3 more in the middle, and 4 more at the end. So in the end, I have a total of 9 w's that are being multiplied together, and I can rewrite this as w to the 9th. The general rule that we work with here is when we are multiplying the same base raised to different exponents, the shortcut is that we can simply add the exponents together. So a to the n times a to the m is a to the n plus m. People will often refer to this as the product rule for exponents. When you're multiplying the same base, you add the exponents. The second rule that we will work with involves having an exponential expression inside parentheses with a second exponent outside the parentheses. Again, to understand what any of these expressions mean, we can go back to what an exponent means. In having x to the third raised to the 4th power in part E, I know that the 4th power is telling me I'm going to have 4 of these x to the thirds multiplied together. So x to the third in parentheses raised to the 4th power means x to the third times x to the third times x to the third times x to the third. Well, using our previous rule, when we're multiplying the same base, we can simply add the exponents. 3 plus 3 plus 3 plus 3 is 12. So I know I have a total of 12 x's. In part F, 7 to the 6th raised to the 3rd power. That 3rd power is telling me I will have 3 7 to the 6th multiplied together. Again, using our product rule for exponents, 7 to the 6th times 7 to the 6th times 7 to the 6th tells me I can add up those exponents of 6 plus 6 plus 6. I have a total of 18 7s being multiplied. Now, while writing these expressions out did work, it took extra time, and it would be nice if there was a shorter way to think about this or approach this. So if we go back to the original expressions and ask ourselves, how could we get from the exponents of x to the third raised to the 4th in part E to the answer of 12? Well, we notice that the 3 and the 4 multiply to make 12, because 3 times 4 means 3 plus 3 plus 3 plus 3. And the same thing in part F. If we were to multiply the 6 and the 3 together, we get 18, because 6 times 3 means 6 plus 6 plus 6. So in looking at part G, 3 to the 2nd power in parentheses raised to the 6th, I don't need to rewrite 3 squared 6 times. I know that I'm going to have a bunch of 3's, but if I were to simply multiply the 2 times the 6, I'd end up with having written out 12 3's. So 3 squared to the 6th power is 3 to the 12th. The general way that we state this rule We call this the power to a power rule. A to the n in parentheses raised to the m. When you have an exponent in parentheses raised to another exponent outside parentheses, we simply multiply the exponents together. So a to the n in parentheses to the m becomes a to the n times m. The third multiplication rule for exponents involves having a multiplication or a product inside the parentheses with the exponent outside the parentheses. So in part I, 5t in parentheses to the third power, again we go back to what this means. The exponent of 3 on the parentheses tells us that whatever's in parentheses will be repeated a total of 3 times. So 5t quantity to the third is 5t times 5t times 5t. Now, knowing that multiplication is commutative and associative, I can regroup the 5's together to notice that I ended up with a total of 3 5's being multiplied, so 5 to the third. And separately, I have a total of 3 t's, so I can rewrite that as t to the third. So 5t quantity to the third became 5 to the third t to the third. Looking at part J, we have 3xy in parentheses raised to the fourth power. Again, that fourth power tells me whatever's in the parentheses will be repeated a total of 4 times. So 3xy to the fourth power is 3xy multiplied by itself 4 times. And when I write this out, I notice that there are 4 3's being multiplied, there are 4 x's being multiplied, and there are 4 y's being multiplied. So quantity 3xy to the fourth power is 3 to the fourth, x to the fourth, y to the fourth. Our general way of stating what we call the product to a power rule, a times b in parentheses to the n, is that we will apply that outer exponent to each factor on the inside. So we will have a to the n times b to the n.